All right. Hi, everybody. Welcome to our first lecture of Module 2. So this lecture is about energy and also a little bit about enzymes, because enzymes are incredibly important in the transfer of energy from one molecule to another. Essentially, enzymes either build things up or break things down. And it requires the input of energy to build things up, and it releases energy to break things down. And so enzymes are highly and heavily involved in energy reactions in our cells. Now, before we get started, let me just preface this with by saying the idea of energy, like free energy that we're going to talk about, and the idea of entropy, which is energy that's unable to do work with, these two concepts are really tricky. When you get into chemistry, you're going to talk about entropy and you're going to talk about enthalpy and you're going to talk about Gibbs free energy and stuff like that. And it's challenging. So I'm going to do my best to kind of cut the icing off the cake, which is the best part of the cake anyway. And we'll talk about the icing. I hope I don't confuse you too bad. I'm going to do my best to make it succinct and tell you really just what you need to know to be successful. So I'm going to share my screen. Let's get into our Google Chrome, our energy and enzymes. And let's present. Okay. All right, so here we are. How do we harness energy to do work? Well, let's start off with the laws of energy. So we know that energy is a fundamental part of biology, and something to consider is that the source of basically all energetic reactions that take place, the source of almost all the energy that is on our planet comes from the sun. And I know that's kind of tricky because it goes through a lot of steps if you think about it. Like if we're burning coal, like fossil fuels to run power plants to power our devices, it's kind of hard to see how that came from the sun. But if you consider that coal came from living organisms from the Carboniferous period back, 400 million years ago, these giant trees and these big lush tropical forests that covered the earth right when dinosaurs were starting to move out of the oceans. You had these huge tropical forests and there's nothing to break them down. There was no fungi or bacteria that could decompose them. And so, as you guys know now from our macromolecules lecture, cell membranes, it doesn't matter if you're an animal, a plant, or a fungi, cell membranes are made out of lipids, and lipids are oils. And so, you have all these cell membranes that are basically not being broken down and not getting their energy utilized by bacteria and fungi for growth. And they're just sitting there. So, you got these and then there as everything else breaks down because the sugars and the proteins and things like that kind of clean themselves out, you get these layers of just these phospholipid sheets in our bedrock, and that becomes our coal deposits and oil deposits and things like that. And if you consider like where the energy came from to make those carbon-based life forms, well, they were photosynthesizing. They were taking in the energy from the sun and using that energy to build their phospholipid membranes that were eventually burning as fossil fuels. So I know that's a kind of an abstracted way to look at it, but all of the energy on our planet, the objective scientific energy, comes from the sun. Now, energy is not the same. There's many different forms of energy, and we're going to talk about several of them. And then there's like one particular form of energy that is not useful at all. We can't use this form of energy to do work. It's basically the heat of the thermal heat of a system that cannot be captured to do work, and so usually it leaves that system as radiant heat that cannot be captured to do work. So before we talk about that type of energy, the kind that we can't use, let's talk about just the laws of energy themselves. So the first law of thermodynamics is simple. It's like a giant maxim of the universe. It says energy cannot be created or destroyed, but it can be transferred or it can change form. So it gives us flexibility. It gives us rigidity at the edges and says you cannot have any more and you cannot have any less energy than what you start with. But within those boundaries, you can move energy around, it can change forms and things like that. And so that's good because that gives us the flexibility we need to be able to take energy from the sun convert it into chemical energy, and then transfer that to our cells. Okay. This means, so this goes into maybe a quiz question, that a science fiction based reaction like cold fusion, which is this notion that you can generate lots of energy from very inert things, like you can do cold fusion on water and create just like these huge power plants, or you can do cold fusion on, I don't know, I forget. I don't know. It's been a long time since I've read those science fiction novels, but that's the idea of those novels, is that you can produce immense amounts of energy from seemingly nowhere, and that's not possible. You cannot create or destroy energy. You'd have to get it from somewhere else. That's the key. All right. So what is energy? What is this stuff we're talking about? Well, let's just give you the idea. Let me give you the breakdown of the two types of energy. And the first type is free energy. So free energy is energy that can be harnessed to do work. I should have an ed at the end of harness. I just realized that. Okay. We represent free energy with the variable g. And so BGs, staying alive. The G represents Gibbs free energy. So that's where the G comes from. And generally, we talk about free energy in terms of joules, but we can also talk about it in terms of calories, which I'm a big fan of doing. So if you're into nutrients and nutrition and macros and things like that, you talk about G all the time. You just talk about it in terms of calories. You say, hey, if you take in more calories than you're burning off through your metabolism, your base metabolism, if you're taking in more calories than you're burning off, guess what? You're going to pack on weight. If you're burning more calories than if you're burning off more calories than you're consuming, well, then you're going to be in a negative state. So you're going to lose weight. And so this is the same thing. I mean, we're essentially talking about the same exact thing. So anyways, that's free energy. Free energy is energy that can be used to do work, and a useful way of thinking about it is like calories. Like there's plenty of mass in a bowl of cereal that you're not going to get any energy out of, but there's plenty of chemicals in the bowl of cereal that do have free energy in their bonds that you can capture and harness to do work. The other type of energy is the one that I was talking about before. It's the tricky one. Entropic. So entropic energy is thermal energy that cannot be harnessed to do work. So thermal energy in a system. So the thermal energy is this. Okay, I'm going to give you a breakdown of this. And I'm going to try to do the best I can to make it succinct, but also make sense. Okay. The way that we talk about temperature today is we say 0 degrees is sort of relative. Like we say, okay, 0 degrees is the temperature at which water freezes, or 0 degrees is the temperature that's super cold. And then from 0, we can say, oh, is it negative, like 20 degrees Fahrenheit or Celsius? Is it positive degrees, 20 degrees Fahrenheit or Celsius? And so the 0 becomes a relative marker for what we think about when we talk about temperature. But the truth of the cosmos is that 0 is placed way up on the thermometer spectrum of the universe. It's 400 and something degrees away from 0, like for objective 0 degrees, 0 degrees, like the bottom line, the coldest you could ever possibly get in this universe is 400 degrees less than what we call 0. But that's confusing. Like, who wants to talk about it like that? And so those units are called Kelvin, and you don't really hear about them much unless you're a scientist. Usually we hear about things in Celsius and Fahrenheit. But again, those are like 400 degrees hotter than Kelvin. Okay, now that you know Kelvin exists, at 0 degrees Kelvin, matter stops moving. There is no thermal anything in matter. It becomes dead, completely inert. No movement whatsoever, no vibration in that matter. It's essentially just inert. Okay. As you add temperature to material, so like your keyboard, your t-shirt, when you walk out, if I walked outside right now, my shirt would get warm. When we add energy to materials, it raises the thermal energy of that material. Everything around you that you like interact with on a day-to-day basis, like water bottles, t-shirts, cars, even outside, the air outside, all of that is Oops. Sorry. All of that has a great deal, hundreds of degrees of thermal energy within it. It's just we don't talk about it in the scale of Kelvin. So usually we're just like, oh, this water bottle is like 40 degrees. Well, that's pretty cold. This water bottle is like 70 degrees. Microphone's 20 degrees. Why do I keep saying 20? I keep thinking in Celsius. That's why. So, anyways, that's the idea, is that every object, everything with mass has a certain degree of thermal energy in it. So, what is entropic energy? Well, that's any of that heat that's in a material that cannot be harnessed to do work. Usually, it will leave that system in the form of thermal radiation, like in the form of kind of long wave electromagnetic radiation, and it won't be able to be harnessed by anything to do work. So that's kind of the idea. All right, let's move on to the different forms of energy. Oh, we were just finishing this up. So this is a very simple equation. It's just saying that free energy is mutually exclusive from entropic energy. When we talk about free energy, we're talking about things that can be energy that can be used to do work. Entropic energy is energy that cannot be used to do work. And so if you take those two different forms of energy and add them together, you have the total amount of energy that's in the cosmos. Okay. Where was I? Okay, so let's talk about the different types of free energy. Now, forms of energy, that's forms of free energy. So we have things that we're familiar with, like we have, let me get my pointer out. We have nuclear energy. Nuclear energy is what's fusion, which is crazy, is what's taking place in suns and stars. Fusion is the idea that you have hydrogen that is under so much pressure, gravitational pressure by the masses of hydrogen around it, that it collapses in. Two hydrogen nucleuses collapse in on each other. They overcome the strong or weak nuclear forces. They collapse in on each other. And that collapsing in on each other, the combination of two atomic nucleuses together, releases so much energy that you have basically a star is a nuclear reactor. And then you have fission, which is taking place inside the Earth's core. So that's where you have very heavy elements that are radioactive, and they release little chunks of particles every now and then they slowly lose mass over time. And that's the idea of nuclear power. Okay. The ones that we should really focus on, though, are kinetic and potential and electromagnetic. Thermal, I already talked about thermal energy. Um, we're gonna talk. I like thermal energy is associated with entropy, but I really want to focus on kinetic, potential, and electromagnetic radiation. Kinetic energy is the energy of moving mass. Kinetic energy is if you have a car moving down a street, you have a several thousand-pound car at a velocity. Now you have kinetic energy. As soon as that moving mass meets another mass that is not moving at exactly the same pace and direction, boom, there's going to be a transfer of energy between those two masses, and so collision, that sort of stuff. That's the energy of sort of moving mass kinetic energy. Now, electricity is the same idea. It's moving mass. It's just a certain particle of mass, or a particle with mass. So we're talking about just electrons when we're talking about electricity. Now, electrons, even though they're like one of the smallest particles ever, they still have mass. So you still put them on a scale, they're going to weigh something. They have mass. They cannot go the speed of light. They have mass. But electricity, electrons moving down a wire, is a form of kinetic energy because it's mass moving down a wire. So you get lightning, power lines, that sort of stuff. Those are the two different types of kinetic energy. And so you have some examples of those if you want to write those down. Potential energy, we can think about it as maybe a compressed spring, or a rubber band that's pulled back. You can also think about potential energy as being chemical, like the one that's shown here. So that would be potential energy that you can't really see it. So like a battery, a battery is just sitting there, it's charged full of electrons. If you connect one into the other, boom, you're going to get a flow of electrons. But a battery, you can't look at it and say it doesn't glow in the dark. There's nothing to indicate it has a lot of energy. Same thing with an apple or a banana. These things are all stored forms of energy, so they're not really visible. You can see kinetic energy, right, in the form of lightning or electricity and the products of electricity. You can see a frog jumping. You see arms moving. That you can see, but potential energy you almost can't see it. Because it's stored energy, it's latent energy. And so a good example of potential energy is chemical, like foods you eat, apples, bananas. It could be somebody, a car on top of a hill, just sitting up there, and you just, now it's potential energy is converted to kinetic energy as it rolls down the hill. And okay, now let's talk about electromagnetic radiation. So electromagnetic radiation is the energy of light. Just think about it like that. Now light comes in a huge spectrum, only some of which you can see. So things that you can see that deal with light are the colors like red, yellow, orange, green, blue, and purple. That's what we're familiar with when we're talking about electromagnetic spectrum. Things that are on that spectrum that you're still familiar with would be things like X-rays. Now, X-rays are a type of light. You can't see it. And the reason you can't see it is that the wavelength is so short that it doesn't even interact with your retina as it goes through. So you can't see an X-ray. Also, so something maybe a little bit longer of a wavelength would be like a radio wave or a microwave. These are light waves. Literally, they're light waves, just like what you're able to see, why you're able to see me, like your eyes can see me. It's a light wave, but it's just outside the spectrum of visibility. And so a radio wave is traveling at you just like somebody's headlights on their car. It's just you can't see the radio wave. It hits your radio transceiver and you're able to listen to music. It's kind of crazy. I still don't understand how that works. that's a miracle of modernity. Okay, so the type of electromagnetic radiation is dependent on the wavelength. So if it's going to be a really high energy wavelength, it's going to be really short. So the shorter the wavelength, the greater the amount of free energy it possesses. The longer the wavelength, the less free energy it possesses. Now, let me try not to confuse you, but we're going to we're going to slice down a layer. Okay. Shorter wavelengths have greater amounts of free energy. Longer wavelengths have less free energy. Okay, remember when I said entropy was the thermal energy of a system of some material, the thermal energy of this material that cannot be harnessed to do work. And often that thermal energy that's in that system that gives it its temperature will leave that system. It'll radiate away from that system as as electromagnetic radiation. So infrared or even longer wavelengths so long you can't see them. They're coming off of your bottle. They're coming off of whatever you have in front of you. They're giving it off as they try to match the temperature of the room as they go towards equilibrium with their environment. And so that jettisoning of its energy through like very long waves of light, that's entropy. Okay, so hopefully I didn't confuse anybody with that. All right, so those are what we got there. And so there's this sort of paradox with free energy transfer. So the thermal energy that's in my water bottle makes it about 70 degrees Fahrenheit. If I have the AC on and it's cranked way down, the room is going to be like 65 degrees Fahrenheit, so about 5 degrees cooler. Because the environment is cooler than my water bottle will spontaneously, on its own, give up its free energy, or it'll give up its thermal energy as entropy to the system. And then it will slowly cool off until it reaches the temperature of the room. Now, why is that important? Well, whenever free energy is transferred from, went the wrong way. Whenever free energy is transferred from one form to another. So anytime you're combusting gasoline in the engine of your car and transferring that combustive energy into pistons, into your drive shaft, into your axle, differential, to your axle, to your wheels, as that energy is transferred into kinetic energy, some of the energy will become entropic, meaning it will become thermal energy that will be captured by the system. It'll get hot, your car gets hot, but you cannot set up a device that will capture your car cooling off to its environment once you turn it off. There's no way to set up any sort of capture device. That thermal energy that is absorbed by your car's engine and whatever else surrounds the engine to make it hot, that thermal energy that's captured from the combustion of gasoline, if you were to take that quantity of energy and add it up with it and compare it to the quantity of energy that was expended when it was transferred energy, you say, okay, so this was the amount of calories. We can do this. This is the amount of calories that's in my gasoline. I can convert those calories into miles moving this weight a certain distance, right? I can convert that into kinetic energy, into some moving mass over some distance, and say, okay, that would have expended so many calories. And then I can say, okay, the difference of that, because I burned up all my gasoline, I went a certain distance. The difference now is in the thermal energy that is now in my car, in my whole system. I burned up that entire tank of gas, but some of that combustion was lost to the environment. It wasn't transferred into the movement of my car. It was captured by the engine in the form of thermal heat. Now my car will cool off to its environment, and it will give off long radiant wavelengths of light while it's doing that. So that's kind of the paradox of this free energy thing, is that some of it's lost to entropic. So consider this: if that happens on its own, this is the paradox of the universe. If every time energy is transferred from one form to the other, some of it's lost every time, then eventually, if you have enough reactions, eventually everything's going to be entropic. Everything will be entropic. All of the free energy will have been transferred from system to system, and every reaction will have lost a little bit of that free energy to entropic energy, thermal, right? Thermal heat, radiant. And that's why you get the heat death of the universe. That's like, oh, that's sort of an eventuality. And so that's where we get the second law of thermodynamics. Bam. Okay, it states this clearly. It's a fact. Free energy will spontaneously become entropic energy in a closed system over time. The universe is the best example of a closed system that we have. A closed system is one in which energy does not come in and energy does not go out. Okay. Free energy will spontaneously become entropic in that closed system over time. That is a maxim. That's a law of thermodynamics. You know how damn hard it is to get something to be a law in science? There's like the law of gravity. That's about it. That's how hard it is. Okay, so anyways, we still need to find what an open and closed system is. So we said this free energy transfer will become entropic in a closed system over time. Well, what's an open system then? Okay, well, if a closed system doesn't let energy in or out, an open system by nature is going to have to be one that lets energy come in or energy leave it. And so that gives us two different types of systems. We delineate these two types of systems because most things that you're familiar with are open systems. The whole universe, though, is a closed system. And so when we look at the eventuality of everything becoming entropic on a grand scale, it's like, oh, okay, I can see how eventually everything, like that law encompasses everything. Like, so the second law encompasses everything. And then within that second law, where everything will eventually become entropic, you have this idea of energy transfer. So energy can come from like some little system inside of the big closed system. You can have an open system that takes energy from outside itself and uses it to do work. That's totally fine. That works just fine. And so that's what we live on. We live on a planet that's an open system. Solar radiation is coming in all the time. Some of that light energy that hits our planet warms it up and creates thermal energy. Some of that thermal energy gets lost to outer space and radiates away and will never be captured to do work and becomes entropic. And so our planet is really just a free energy processing center that is constantly radiating entropic energy out to the universe and will eventually cool off and all that stuff and the heat death of the universe, yada yada. Okay, a closed system, which we said earlier, and I'm just reiterating, is one that does not allow energy to come in or out. And there's only two examples I can really think of. There's a hermetically sealed room where nothing can get in and out, and the entire universe itself. So, not that many things are closed systems, but something to consider. A system that's open will behave like it's closed as long as no energy is coming in or out. Think about that. So, if you have a system that's independent of, it's an open system, it would allow energy in if it could get it, and it would give off energy if it could give it off. You have this system, and maybe we can use the human body as an example. So you have this open system that can take in food and stuff, but if it doesn't take in any energy, any free energy from its environment, it will behave like a closed system and become completely entropic over time if it's not fed. Your body will die, decompose, and turn into dust if it's not fed, if free energy doesn't come into it. And so that's where these things get a little bit confusing, is it's like the universe is a closed system that has this operator that's like, okay, any reaction that takes place is going to lose some energy from that reaction in the form of entropy. Eventually, all that entropy will stack up and the entire universe will be just a giant, cold, vacuous dump. That's the second law. Inside of the second law, we have the first law, which is like, okay, if you're an open system, you are in good shape because you can take energy in, use it, and process it, despite the fact that all around you and inside of your system, everything is proceeding towards entropy. Whew. Okay, hopefully I didn't confuse you guys on that. I know it's super deep. It's kind of like need to be in like an altered state of consciousness to like absorb this stuff. It's like we might as well be talking about like mystical Eastern philosophies. Okay, so if a system goes from a high energy state to a low free energy state, what would be the change of free energy? And how would we represent the change in free energy of that system? Okay, well, we could take the final energy, the energy that you end with, okay, and we could, hold on, I'm going to make sure I'm in the right spot. Okay, delta G of a system, you take the amount of free energy that's left over at the end of a reaction, and then you subtract the amount of free energy at the beginning of the reaction. And so for all spontaneous reactions, for all reactions that would occur on their own in a closed system, all reactions that kind of go from start has high free energy, end has low free energy, all of those reactions are going to happen spontaneously, and they will be represented by a negative delta G. So a way to think about this, okay, when you see a negative delta G, you know that reaction happened on its own. Now, it might have had to have a push, just like a car sitting on top of a hill is just sitting there. And if you just push it, now you've released all the energy of that system. And so even though some reactions, even though they're spontaneous, some of them require just a little push to get them started. But once that reaction starts, it's until it's done. The idea there is that you're losing free energy from the beginning of the system toward the end of the system. Eventually that car is going to like coast to a stop. That all of the energy will be gone. It will be transferred in the form of heat friction between the tires and the roadway. And then the roadway will radiate that heat, that entropy. Oh, okay. Blowing minds. My own in particular. Okay, so we got delta G is always negative for a spontaneous reaction. Okay, let's take a look at that. So in this particular instance, you have a guy on a diving board. That guy is like the car at the top of the hill I was talking about. You have a cluster of molecules together in a big space. You have a very complex molecule like glucose on the right. Now, spontaneously, nothing has to happen. Maybe somebody has to push the guy off the diving board, but that guy, he's going to fall. Okay, so somebody pushes him off the diving board, falls spontaneously. Now he's got less free energy. He's closer to the center of the earth. Those molecules inside of that big chamber, they're just going to spread out. They're going to find random distribution within that volume, within that space. That's spontaneous. Now they have less free energy. You have your glucose molecule. Will eventually turn into carbon dioxide and water. Just if it's sitting there for long enough, it'll break apart, and there you go. Now it's gone from a highly complex molecule to a bunch of non-complex molecules. So what can we see? What is the trend that we can attach to this movement? Well, we could say if you look at the molecules up here with more free energy, okay, if you're looking at the molecules up here, okay, maybe not the guy on top of the diving board, that's sort of representative, but if you look here, we see all these molecules that are clustered together, and they eventually become spread out. We see one molecule become many molecules. So what this tells us is that systems with a lot of free energy are going to be highly ordered, very conscientiously put together. For instance, take a bunch of Legos, shake them up, they're in a box loose. You could shake that box over and over again, and those Legos aren't going to build themselves. But if you take some energy and you put it into that system and you build these Legos all the way up into a giant tower, beautiful, intricate tower, you've just added order to that system. You've added free energy to that system, at least according to Gibbs. And the reason why you know this is because spontaneously, without any sort of intervention from you, just the vibrations in the air and the light around that Lego tower, over the course of time, spread it out in time, that Lego tower will spontaneously break down into individual Lego blocks again, never to rebuild itself. That's the second law of thermodynamics. That's what we know. We know that if you pick up your room and put everything away, just random bumping into stuff, right? I pulled the shirt out of my drawer, I shut my drawer, but the shirt shifted in my drawer. I put my shirt next to the laundry basket moved. The next time I throw clothes at it, it lands on the floor. Over the period of time, just the random bumping into things become random and disordered. That happens spontaneously. That's all we're seeing in these pictures, is that these things will happen. These spontaneous reactions will happen over time on their own. And they always end up with less free energy. Okay. So let's take a look at chemicals and how free energy is distributed and moved around in a system due to chemical reactions. So there's two types of chemical reactions that I want you guys to know. I'm going to just load them up on the board and talk about them. Okay, the first one I'm going to talk about is the building process, and that's endergonic. So that's the first reaction, where the total free energy of a system actually increases from start to finish. You might say, okay, well, that would not happen in a closed system. You are correct. Endergonic reactions must take place in an open system, and we'll talk more about that on the next slide. Okay. But endergonics, where the total free energy of a system increases from start to finish. So that means you have more free energy at the end than at the beginning. They're called endergonic or anabolic. So you think anabolic steroids, right? They build muscle, right? That takes a lot of energy. The other type of reaction is exergonic. That's like the ones we just talked about, with the guy falling off the diving board, the molecules dispersing in space, your room becoming messy over time. Those are all exergonic, where the total free energy at the end is less than what you had when you started. Okay, so the delta G for the building, the anabolic process, is positive. You're adding free energy to that system over time. The delta G for a destructive process is always negative. Okay, so let me show you what these are and we'll compare them in columns, and I like doing it like this. So endergonic reactions, the building ones, the anabolic ones, require energy to come from an outside source. So that could be like, I just worked out really hard, I'm very hungry, I need to repair my muscle tissues, so I need to do a lot of building of tissues, some anabolic work. So I'm going to go grab a protein powder and an apple or something. I'm going to go go put calories into my body and nutrients to give my body the energy and the equipment and the, what would you call them, like lumber and nails, if you will, to rebuild or do an anabolic endergonic reaction within me to build myself up, to repair myself. Like I said, it has to happen in an open system, so energy will come from an outside source. Delta G is always positive, and that reaction is anabolic or building. And so I use the example of going from monomers to polymers. So if you're rebuilding muscle fibers, you're going to need a lot of individual amino acids, monomers, and then you're going to polymerize them into new fibers that will become the repaired tissue. So simple, individual to complex, or random to ordered, or disordered to ordered, or dirty room to clean room. Exergonic is where free energy is lost from a system. So exergonic will happen spontaneously on its own in a closed system over time. Rooms get messy, people fall off of diving boards, cars roll down hills, houses. Dude, the idea of exergonic reactions is literally the law of impermanence. It's like, yeah, all structures are flimsy. Everything will eventually decompose over time. Everything. All of these structures and buildings that you are so familiar with in your life, everything that you see that has a sense of permanence is actually impermanent. Social media posts, local news, all of this stuff is going to happen and change spontaneously in this closed system of the universe over time. And so what ends up happening is everything succumbs to the second law of thermodynamics over time. Everything eventually breaks down. And that breaking down, that loss of free energy, makes the delta G and the change of free energy in that system negative. It's considered catabolic. But here's the coolest part about it is that we're going to bring in some Eastern philosophy. You have to destroy before you can rebuild. There's a catabolic tendency in the cycle of evolution. You have to have a destructive, if you will, a Shiva, right? Shiva is the destroyer. So Shiva destroys what is not useful anymore and then is reborn again, and that's the resurrection myth, in some new form that is better than the previous one that needed to be destroyed before the new one could arise. So, for instance, you eat an apple, the apple is broken down and destroyed within your body, but then you are rebirthing yourself in a way by repairing tissue and cells using the energy captured from the death cycle. Okay. Hopefully that wasn't too deep. Okay. This is the stuff that goes on in my head all day long. So happy, so excited to share it with people. Even though like you're not here with me right now, I'm just talking to a screen. Strange times, my friends. Okay. So breaking down, stuff falling apart. That would be going from polymer to monomer, from a very complex thing like a big Lego tower to individual Lego pieces, from a glucose molecule down to just carbon dioxide and water. And so I have graphs here to show you and illustrate what's happening in each one of these reactions. So this is an exergonic. This is going to happen. This is, you get a building, and over time that building is going to break down. So the arrow of time is the x-axis. The progress of the reaction is the x-axis. That's the movement of time. Free energy. Oh, poop. Hold on a second. I just want to make sure that my video did not stop recording. Okay, cool. It's doing this. Okay, I just want to, sorry, my WebEx acts a little weird sometimes, and it hides like the menu bars and stuff. And then here's the crappy part: is sometimes it said if nobody's in my meeting with me, like you guys, it'll just turn off the meeting. It'll stop recording and give a 2-minute timer. But if I can't see that 2-minute timer, it'll do it, and I'll just keep talking, and then we'll have to go back and record some of this. So sorry, that's what I was fixing right there. Okay, so this is a graph that illustrates exergonic reactions over time. So we said time is on the x-axis, the amount of free energy in the system is on the y-axis. And so at the beginning, you have this big tall building, you have this beautiful Lego tower, and then over time, spontaneously, that Lego tower will become destroyed. It'll become smaller. The big buildings crumble. And that process releases free energy from that system. So you got a big glucose molecule here. You got to break it down in your body. You end up with carbon dioxide and water on the other side. Oh, I see what happened. Okay. Sorry, guys. I don't mean to be doing this. Okay, sorry, I was being weird again. Okay, so anyways, this energy that's lost from this system when things break down can be captured and used to power other open systems, right? That's what we're going to do with metabolism. We can see that the amount of energy from the reaction changes in a negative way. It goes from a higher state to a lower state. So we subtract the end state, the amount of energy at the end, we'll call that like 10, and we subtract 100 from 10 and we get minus 90, and so that's a negative delta G. All right, endergonic reactions are, damn it, it did it again. That's really frustrating. I'm sorry, guys. Okay, endergonic reactions are ones where energy has to come from an outside source. So the energy entering this system could literally be coming from this system. It could be, oh, we're breaking down some glucose, and then that energy is going into the system to take some amino acids and make some muscle tissue. And so you can couple these catabolic reactions with anabolic reactions, or exergonic with endergonic reactions. And in fact, that's what we're going to do in metabolism. So we can ask the question, okay, in the body, if that's what's happening, if we're breaking down the apple, and we're getting this energy is going to power us building a protein, what form is this energy in? Like, what molecule is supplying this energy? I'm going to show you. ATP. Okay. ATP is the primary cellular battery that is hydrolyzed inside a cell to fuel endergonic reactions. There are many types of cellular batteries. And I'll show you them on the next slide. But this particular one is the cellular battery that powers 99.9% of reactions in the cell. This one has the least amount of energy out of all of the cellular batteries. Now you might say, wait a second, what's a cellular battery and why are we talking about them? Okay. There's certain molecules in the body that are like rechargeable batteries. What's cool about them is that you can take an apple, break it down, and charge up this battery, and then use this battery to go power another reaction. There are a couple different types of batteries. So you know how we have AAA, AA, C batteries and D batteries. Well, this is like a AAA battery, and AAA batteries power everything in the cell. If we talk about them in terms of currency, like we say, like energy equals money, we would say this one is a dollar bill. The other batteries, maybe they're like $2 bills or $5 bills. So we'll do. Sorry. Okay, where were we? All right, so we're still kind of on that first line of where we say ATP is a cellular battery, the primary one that's hydrolyzed to fuel endergonic reaction. All I'm showing you here is I'm showing you the hydrolysis of ATP. So you got a 3-phosphate nucleotide. Yes, it is a nucleotide. It's an RNA nucleotide. Don't let us go down that rabbit hole, right? It's an RNA nucleotide that will become hydrolyzed, and it'll have a phosphate group pop off. And that phosphate group typically is not just left and floating out in solution. If it was, then the energy that was once contained in this molecule is lost. Usually the energy that's in ATP is contained in that phosphate group, but it's transferred with the phosphate group to something else. So ATP is a molecule that has a lot of free energy. It's a dollar's worth. You can buy a lot with $1. You ever been to a dollar store? You can buy a lot with $1 of energy. And so what's going to happen is it's going to get hydrolyzed, and that phosphate that pops off, this one over here, usually gets transferred to an enzyme with the energy that's over here. And I keep waving over here, but with the energy that's over here, it's usually transferred with that phosphate. So that plus sign is usually gone, and the energy is usually surrounding this phosphate as it gets attached onto something else. Okay, like I said, it gets attached. There you go. Okay, now since energy is released from the reaction, what is the sign of delta G? You have to know this. You have to be able to flesh it out. I'll give you a hint. Spontaneous. ATP will spontaneously lose a phosphate group, and become ADP over time. And the energy with it will just... Okay, so it should be a negative delta G. All right, here's our cellular batteries. So this is back to our ATP is the primary cellular battery. Okay, there are many types of cellular batteries. The $5 bill one, that's the biggest one we got, is NAD or NADH. It exists in two different forms, and we'll talk about reduction and oxidation in just a second. The reduced form is the charged up one. That's the one that has the energy. The oxidized form is the one where it's a dead battery. So all of these batteries over here, so you can think about these as you've got AAA batteries, AA batteries, and C batteries. Maybe this is a D battery, but it's in plants, so we're not really dealing with that right now. Okay. Oh, there it is. It's a dollar bill. Okay. So you got $1 bill, $2 bill, $5 bill. These are batteries as well. The oxidized form of a battery does not have any free energy. It's dead. It needs to be charged up. Yeah. We've got flavonoid adenine dinucleotide, or FAD, or FADH2 is the charged up form. FAD is the uncharged form. In plants, you have nicotinamide adenine dinucleotide phosphate, or NADP. It becomes NADPH when that battery is charged up. Now, this is the important part. All these cellular batteries can give and receive free energy in the form of stored electrons, just like regular batteries. That's why I call them batteries. You're never going to hear somebody call them cellular batteries again, but they are cellular batteries. And I think to connect something abstract, like a freaking, like, I don't know, whatever these things are, right? These energetic molecules, to try to connect them with something that is analogous to something familiar is super helpful. At least it was for me. So we said they can exist in these charged forms or uncharged forms, reduced or oxidized. They can give electrons or they can receive electrons. So if you're a dead battery, you can receive electrons. If you're a charged up battery, you can give electrons. That's how I want you guys to think about these things. Okay. So like we said, ATP is widely used to facilitate reactions in the cell, especially endergonic ones. Most reactions cost less than $1. You can buy a lot at the dollar store, and reactions don't give change back. So that means that NADH and FADH2, in order to be optimal for the cell, because most reactions cost less than $1, and these are a $5 and $2 bill respectively, we need to be able to convert this $5 bill. We need to find a change machine is what we need to do. Yeah. And so that exchange that we're going to do is done deep inside the mitochondria, and we will cover that next lecture. Okay. All right. Most exergonic reactions, although spontaneous, usually take a long time to break down on their own. They need something to jumpstart the reaction. This usually comes in the form of a biological catalyst. Now I'm getting ahead of myself, right? I had a bunch of examples there, but I'm going to skip those examples. We don't really need them. All right. A catalyst is a chemical agent that helps speed up the rate of the reaction without itself being changed. You have a catalytic converter on your car. It's made of heavy metals. It's just behind your bumper. And what it does is it burns up, it combusts uncombusted gasoline. So as this uncombusted gasoline, which has free energy in it, goes on by, those heavy metals combust it. They help it react with oxygen, and poof, out it comes as a less free energy state. So the gasoline comes through, it combusts by the catalytic converter. The catalytic converter is unchanged. The heavy metals are still there. They just help to facilitate the uncombusted gas combusting with oxygen. Okay. Let's think of some real life catalysts. Well, that was one. A match is sort of a catalyst. That push, like the car that's on top of a hill, little push to get the car down the hill, that would be a catalyst. So biological organisms have their own versions of these catalysts. And so for every possible reaction that you can think of in the cell, there is a special type of catalyst that moves it forward. And these this family of biological catalysts are called enzymes, and they're made out of polypeptides. They're made out of proteins. And proteins, if you remember from previous lectures, how you make a protein is coded for in your DNA. So those protein catalysts are called enzymes. Now, enzymes will help to lower the amount of energy it requires to help push the car down the hill. So that's one way to think about it, right? Is that the car sitting on top of a hill and it has a lot of potential energy and you just want to push the car to get it down the hill. And so enzymes are essentially the body's way of making you not have to push the car as hard to get it to just blow up, to get it to go down the hill. And so that's a good way to think about it. Enzyme names, it's not in the notes sheet, but it's important. And whenever you see an ASE at the end of something, so it could be catalase or transcriptase or polymerase or things like that, those ASEs at the end signify that it is an enzyme. Okay. Sucrase. All right, let's talk briefly just about redox reactions before we jump into this E sub A thing, which is the energy of activation, or the amount of energy it requires to push a car down a hill. Okay, so during electrons that are transferred from one molecule to another molecule also transfer energy with them. And so whenever we take like an electron away from a molecule, we say that molecule is oxidized. So whenever an electron is moved between molecules, we say a redox reaction has taken place. So why are I'm just going to open these up. Why are redox reactions important? Here's why. In the molecules that are contained within an apple, there are a lot of free energy contained within those bonds, within those molecules. So you have a molecule like glucose, and the carbons bonded to the hydrogens in glucose provide a lot of free energy availability. It's an opportunity. It's potential energy that we can capture. What we do in the body is we break this apple down and this glucose very, very slowly. We manipulate, we twist it just a little bit at a time until it pops off one of its electrons. And we capture those electrons. As we start to break glucose down, it releases electrons, and we capture those electrons with our cellular batteries. And so what happened, why we're saying reduction oxidation, when glucose is losing electrons because it's being broken down, those electrons are leaving glucose, which means glucose is becoming oxidized. When water reacts with iron and iron rusts, it loses electrons to oxygen. The iron is becoming oxidized. Nitric, or what is it? Ferric oxide? Now I sound like an idiot. It's like FeO2 or something, right? It's the rust. So anyways, rust is oxidation. It's the oxidation of iron. Reduction, the other side of that, where if you're gaining electrons, anytime you're gaining an electron, that's usually adding free energy to your system. So consider the battery. When we add an electron into a battery, we just reduced the battery. We reduced its charge. It now has one more negatively charged thing in it, so it's been reduced. And so that battery now has more free energy in it. And so whenever electrons are transferred, there's a redox reaction taking place. Okay, so whenever one molecule is reduced, it usually means another molecule is oxidized. All right, during digestion, food is broken down. I think we already talked about this. We'll skip this. All right. So during digestion, food will be broken down, and the energy from the food will be transferred to cellular batteries by enzymes. This process of breaking down food is spontaneous or exergonic, meaning there will be less free energy in the system at the end of the reaction than at the beginning. During the transfer of energy from food to batteries, heat is lost, radiates away from your body. The release of energy in the form of thermal radiation is what keeps your body temperature constant. Okay, I basically already spoke to that just right before it when we were talking about reduction and oxidation, is that you're breaking down food, capturing electrons from the food you're breaking down in cellular batteries. Those cellular batteries can then go power anabolic reactions. It can go provide the electrons to help build things up, to make big polypeptides and make muscle fibers and things like that. The transfer, there's transferring energy going on here. And remember, anytime some energy gets transferred from one form to another, some of it's lost. And that little bit that's lost is in the form of thermal heat. And so what we end up having is we end up creating thermal combustion engines in our bodies as we're stripping away electrons from glucose and then using those electrons to power up building operations in the cell. Energy is being transferred, heat is being lost. Your body is radiating heat. Now, your body has a thermal temperature that is greater than its surroundings. That thermal temperature is maintained by the reactions taking place in your body. But your body, if it stopped doing those reactions and behaved just like a closed system, nothing comes in, would start to lose heat and cool off because it's unable to maintain its temperature. Okay, so let's talk about glucose. Even though glucose is like a super energetic molecule and we get it from the food we eat, it will break down into carbon dioxide and water on its own. So we'll have glucose here. It will break down into carbon dioxide and water on its own, right? You see how delta G is less than 0 over here? That's a spontaneous reaction. That can happen on its own. But just like a car sitting on top of a hill will spontaneously roll down the hill, it's got plenty of potential energy. Sometimes it just needs a little push. It's got to go through a transition state. There's got to be a little bit of energy applied to that system in order to make it go spontaneously to completion. And so enzymes can actually help us to reduce the energy required to push the car down the hill, to change glucose into carbon dioxide and water. Enzymes help to speed up reactions and break down molecules like glucose quickly by raising the molecule's latent energy above its energy of activation, abbreviated E sub A. And don't worry if the A is capital or lowercase. That's in Google Documents, you can't do a capital A. It's super frustrating. In a subscript, you can't do it. I've tried. It sucks. Okay, so the energy of activation is just how much energy does it require to be pushed into the car to get it to go down the hill? How much energy do you have to attach to glucose to get it in a transition state where notice the bonds between A and B and C and D are together, but then up here in the transition state, they're shown wavy because they're shaky. It's a shaky bond. And then you shake those bonds, you get them to vibrate to add some energy to them. And then they're able to switch quickly. They're able to switch quickly to the other bonds. So then A bonds with C and B bonds with D, which is a lower energy state. And guess what we're not showing leaving this reaction? Heat. There should be heat, thermal energy leaving this reaction. Okay. All right. So as you can see on this graph, the energy of activation without the enzyme is much greater than it would be with the enzyme. And so the energy required to push a car over a hill with an enzyme is much lower. And what is that? That's conservation of energy. So your body has created these little chemical robots that are able to lower the amount of energy it takes to break things down, but still capture the amount of energy back as it breaks it down. Because think about it, right? You put a little bit of energy in, so that's the energy of activation. So you have to add a little bit of energy to the system, push the car, and then that kinetic energy of the car picking up speed, rolling downhill can be captured by something else. And all of that energy can still be captured, right? Because think, like if I push the car like really hard and it goes down the hill, I could capture that momentum of it picking up speed down the hill. I could capture that momentum with some sort of spring or something. If I gently push it until it goes down the hill, it'll still pick up speed and still press that spring in, and I'm still capturing the energy. The idea, though, is that I spend less energy pushing it really hard, and I spend just a little bit of energy giving a little push, and then I can still capture all of that hill energy back in the spring, and that's what I'm doing here. The body has made the process so efficient that it only has to put in as much energy, as little energy as possible to get it to go to completion, to capture all those electrons in the cellular batteries. And so that's kind of where we're gonna take off from here. We can speed up reactions by heating the reactants up, so we can take glucose and boil it and it'll start to break down. We can heat things up, and so that adds the free energy to the system to bring it above the energy of activation. We can use it also adds, so here's the weird part, it also adds entropy to a system to heat it up. I know it seems weird. You're adding free energy, but also you're increasing the entropy of the system as well. And I know that's a weird concept, but it is what it is. Okay, so use a catalyst. Catalyst can help to lower the energy of activation. In biology, that's an enzyme. So I think we covered everything. So the food glucose is oxidized, right? It loses electrons, while cellular batteries are reduced. They gain the electrons from glucose. Okay, that's basically how metabolism works. So as long as you can get reactants above their energy of activation, the reaction will proceed quickly to completion. And then once the reaction's over and everything's become inert molecules, that's considered equilibrium. It's when the free energy has been converted to entropic energy. And so that system is stable now. Stable but chaotic. I know it's weird, right? Okay, so that's the end of this lecture. Oh yeah, sorry. That is the end of this lecture, but here's a segue into the next one. So there are 3 reactions we're going to study in the cell that require enzymes: glycolysis, Krebs cycle, and electron transport chain. I'm not even going to talk about this right now. You've heard enough. That's where we're going to come to next lecture, you guys. All right, we'll see you then.